Hi, folks. We've been talking about the electromagnetic spectrum, and this time I want to talk about the little tiny piece of it that is visible light. Now, many of you have heard of Roy G. Biv, which is a memory device to help remember the colors that the human eye can see: red, orange, yellow, green, blue, indigo, and violet. The visible colors of the spectrum range in size from about 760 nanometers to about 380 nanometers. They're very small, kind of like the sizes of small microscopic creatures that would be swimming around in pond water. Every unique color of the visible spectrum has a unique wavelength. And the human eye is only sensitive to these wavelengths. Different animals can actually see in slightly different colors. Now, many people thought that color was impurity and that white light was pure. Sir Isaac Newton in the 1700s was the first person to realize this was untrue. He took a simple prism, took some light shining through a curtain, and found that white light contained all of the lovely colors of the rainbow. So he gave us a lot of insight into light. Different colors of light contain different amounts of energy. Low energy photons of light are red, and higher energy photons of visible light are on that blue end of the spectrum. Those little silly cat lasers that we use to entertain our pets, those are low energy, the same ones that are used in checkout scanners. By the time you get into the middle of the visible spectrum, these, if you're talking about gun sights or laser pointers, a little bit more high energy, they penetrate better. By the time you get to the higher energy end of the visible spectrum, as pointers, they can be dangerous. They can potentially keep a pilot from seeing the area, and so people have been arrested for pointing these up into the sky. If someone's going to be doing some laser cutting, you're usually talking about that high energy end of the visible spectrum. So how do you produce the whole rainbow of colors? Well, to do that, you need the right source. Hot solids and dense things tend to produce that entire rainbow, all those lovely colors. The biggest source, of course, that we're used to is our beautiful star, the sun. It is a very, very dense ball of gas, and so it produces that full spectrum. The other source that's common for us is a old-fashioned light bulbs that get hot, also known as incandescent light bulbs. Those are going to give you all of the colors in that spectrum. But if you are using fluorescent lights, which are much cheaper to operate, they stay cool, you are going to notice that not all of the colors of the rainbow are present. If you look, there's a definite big gaps here. And so if the coloring in your world with fluorescent lighting looks differently, that is because different colors are missing. Mercury vapor lights, which are old-fashioned street lights, these also have a tendency to look a little yellow-green. There's a lot of yellow and green in their spectrum, very few of the oranges and reds in this kind of a spectrum, and people tend to look a little ghostly under mercury vapor lights. If you have an individual gas, like if you take any individual element, sodium, potassium, hydrogen, helium, whatever, and you make that into a gas, it will produce specific set of lines. Now, these lines are so cool because it's like a fingerprint for that element. And it helps us identify specific elements and specific chemicals in all sorts of situations. If you've ever wondered, how do they know what elements are in distant stars? How can they determine the chemical composition of things from little tiny samples in a crime lab? Very often what they do is they take those little samples, they burn them, and then they look at the lines of light that come out. They analyze those, compare those to known spectra of known elements and molecules, and that's how they identify them. For stars, they look at the line spectra that come through with the light from those stars, and they use that to identify the elements. So light is useful for lots of different ways. But how do you get a line spectra for a particular element? Well, if you remember, all light is produced by an accelerated charged particle. So in a particular atom, it is actually the electrons that are being accelerated that are producing light. So here's how it works. You've got the protons and the neutrons that are locked in the nucleus of the atom, and then you've got electrons And it was discovered about 150 years ago that electrons kind of exist on unique energy levels. These are places where electrons can be, and then places where electrons can't be. Think of it like a set of stairs. You can be on this step, or that step, but you can't hover in between. You've got to be here, here, or there. So what happens is an electron is sitting happily on a step, happily here, and then he gets energized. He gets hit with heat, light, or electricity. And when that happens, he's got so much energy, he can't stay there. The kinetic energy makes him jump, and he jumps to a higher level, and he jumps to a higher level. Now, when he did that, he left a hole. This is kind of like leaving a front seat open at a Beyonce concert. Somebody's going to fill that seat. Somebody's going to go, hey, there's a front seat open. I want to be there. And what happens is other electrons fall to fill that seat. And when they fall to fill that seat, when these other electrons fall, they give out a photon of light. Now, when these other electrons fall, this guy leaves a hole, so when somebody else falls. When they fall, each time they fall, conservation of energy goes in to make the electron jump. Energy is released when they fall back down. And when they fall back down, each one of these falls is corresponding to one specific color of light. So the distance between these levels is dependent upon the individual element we're talking about. Kind of a quick explanation, but that's how these individual lines get produced. Now, color. The color an object is the color that something reflects. White light contains all the colors of the rainbow, Roy G. Biv. But if you see a red apple, what happens is all these colors hit the apple, but only red light is reflected to your eye. What happens to the other colors? That is absorbed and turned into heat. The green grass and the green trees reflect green, and all the other colors turn into heat. The red viper, it's going to reflect red and everything else turns into heat. The blue dress is going to reflect blue and everything else is going to turn into heat. So the color an object is the color light it reflects. The cool thing is that if a color has got to be present in the light, and if it's not there, you can't see it. Now you might go, okay, so why do I care? That you care because if you have ever tried to color match. Where do you do this in your life? Well, if you've ever tried to paint anything, whether this be a room in your home or tried to paint a car or anything else, if you've tried to match colors, you have got to do this in the correct light. And the reason is, if the color of light is not there, you do a crummy job of matching colors. Let me give you an example up here. Great set of pictures. This green pepper under white light, you can see it as white. But under red light, it looks dark. You can only see the green pepper is green when you see it under green light. Under red light, the white here looks red. And under green light, the white here looks green because remember, white is all the colors of the rainbow and it reflects green as well as any other color it happens to hit it. One of the places this has bothered me is when I've been buying socks. I go to a store, I'm trying to find the difference between black socks and brown socks, and I go to the checkout, and I think I picked up a pack of black socks, and I'm standing there, and I look down, and I go, oh my gosh, I just bought brown socks, because the lighting is not good enough for me to determine the difference. A lot of stores, right above the paint chips, they're going to have full spectrum light. And they do that, the lighting's going to be different to help people do this color matching. Now let's spend a few minutes here talking about light bulbs. Light bulbs in the modern age have gotten a little bit wacky, and here's why. They have temperature numbers on them in Kelvin. Kelvin is this temperature scale that goes all the way down to absolute zero. And if you say 6,000 Kelvin, you're talking about a temperature that is very, very crazy hot. So hot that iron would melt. Well, what the hey? A light bulb's not going to get that hot. I hope it would burn my house down. So what's going on here? Well, this has to do with the temperature is related to color, and it goes back about 150 years. Let me tell you the story quickly. Guy back in the 1800s named Max Planck was studying studying this phenomenon that if you take a piece of metal, those of you who've ever welded or done any forge work, you probably understand this. If you heat a piece of metal a little bit, it will get red hot. But if you put it in that forge and get it warmer, it's going to go from red hot to orange hot to yellow hot to white hot. And white hot is a lot hotter than red hot. Red hot is cool, white hot is hotter. But if you keep adding heat, you will eventually get it blue hot. There's a relationship between temperature and color. The thing that is weird, very, very weird, is this is opposite how you and I think about water taps. When we look at a standard water tap, red means hot and blue means cold. But when we talk about temperature and color, this is the opposite, because blue is very hot and red is the coolest of them all. So when you go to buy a pack of light bulbs and it says that it's got a cooler temperature, that means that the color of light is going to be redder. And if it's got a hotter temperature, that means that the color of light is going to be bluer. So let's try this. Okay, of these 3 light bulbs, which one is going to give you the reddest light? The reddest light. Yeah, this one. This is going to be the reddest light because it is the coolest temperature. Which one's going to give you the bluest light? Yes, this one, because it is the hottest temperature. It has nothing to do with how hot that light bulb is going to get, I hope. That'll burn your house down. We don't want that. And if you want something that's more balanced, more like natural daylight, pick something in the middle. I found this set of pictures online. I think it's a nice image to kind of give you an idea. If you want some lighting in your home that's kind of cool and very blue, go towards the higher end of those Kelvin numbers. If you prefer warm lighting, pick something that's those lower ends. And if you want something that's more balanced, well, stick towards the middle of those Kelvin numbers. All right, you guys, have a fabulous day, and we'll talk to you later. Bye-bye.